The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, well, let me start talking. And I ran out of my slide, since last week. So I was making this new topic, and you will see, I thought I'm pretty familiar with this, but I still struggle a lot. And there is one place I will show where I'm still confused. Maybe you can help me. And that's always related to this electron linear charge that always confuses me. So I struggle a lot. Okay, so today in the first few lectures we discussed the thermoelectric effect, and now we move on to talk about the thermionic engines. And also, I hope we'll have time to discuss related topics from the discussion on thermionic engines, and also hoping to actually jump in to introduce you really how pin junction works. And in terms of Schottky barrier and Schottky diode, that's really just a metal semiconductor interface. Again, I think from the vacuum thermionics, we can probably appreciate the evolution. I hope we will see the evolution, and at the end, the mathematical formulation formula, the expression for current voltage are very similar. Okay. But let me, I need something that we showed before. So this is first the Fermi-Dirac statistics. This was what we did probably the first lecture, the occupation of electrons in a quantum state. And here you can say this is the electron volts, 0.05, 0.1. So the Fermi-Dirac distribution is very narrowly focused near the chemical potential. And if you're away from the chemical potential, the function either the state is fully filled or almost empty. And let me just make a remark. Typically, when we talk about thermionic emission, E minus mu will be few E weight. So we'll be really at the tail end of the Fermi-Dirac distribution. And when E minus mu is few E weight, Kb is 26 millielectron volts at room temperature, you can see that factor of 1 will drop out because it's insignificant. So use this when we derive the Richardson formula. And the other point that I will use in the discussion is the electron number density. So this again we did before. We did a counting of the number of electrons, count all the quantum states. Each quantum state have 2 electrons spin up, spin down, and this is the average number of electrons. 2 states, spin up, spin down. And from there, if we do the exponential drop that 1, we get the electron number density is proportional. Here is, I want to point out T3 halves, right? So we group all this factor into NC, and then it's the difference of the conduction band to the chemical potential exponential. So that's what we had before in terms of electron density. And the other point is to again review that we say what's the difference between metals, semiconductors. In metal, we have the chemical potential fall into the band, and semiconductor has band gap We dope it either N-type or we dope the P-type. Depends on, say, what kind of atoms. For example, we put silicon either boron, which is P-type, or phosphor, which is N-type. And that way we're shipping the Fermi level or the chemical potential. Okay, so those were what we covered previously. And now let's think about if I have a material, metal for example, I want to pull out the electron, right? And if I pull out the electron, the ion background in metal attract the electron. So I have to do some work to pull it out, right? So the minimum amount of work that I pull electron from inside immediately to outside vacuum is the work function. So from the Fermi level, this is a metal, from Fermi level I pull electron, I pull it out to vacuum level, but this vacuum is immediately outside the metal. Okay? And then why I emphasize that, if you think about I have a vacuum, I have positive charge, a negative charge, right? Even both positive and negative charge in vacuum, then the electrical potential at these 2 points, even vacuum, are different, right? Because there is a potential from the positive to negative. So I say this is immediately outside the surface. That's how we define the work function.
For metals, right?
Yes. Semiconductor, we have to use a different terminology. And that's how Einstein got the Nobel Prize, right? So he explained the photoconductivity effect, where the effect was you shine light on metal, and then you get electricity, you get the electron out, so you can measure current. But what was puzzling at the time was that the number of the current not just depend on intensity, but depend on the wavelength of the light. And so there was no explanation, and Einstein then explained you have to have the photon energy larger than the work function to lift the electron out of the metal surface. So the photon energy, of course, is inversely proportional to wavelength, so long wavelength photon is not effective there. So Einstein's Nobel Prize is not because of relativity, which was too radical. These were more or less controversial. And then, in semiconductor, the Fermi level, there's no electron there. When we dope it such the Fermi level fall inside the gap, so there are no electron between the conduction and valence band. The Fermi level is in between. So the way you could lift the electron, but when you lift the electron, usually you lift from the bottom conduction band, which is EC, to the vacuum level, and we give a different name. And in that case, we call it affinity. So semiconductor, because the chemical potential level can be changed by doping, but how much energy you need to lift an electron from the bottom conduction band to vacuum level, that's fixed. So this is a number you can look into tables, the affinity of semiconductors. And typically counted from conduction band edge. So those are the basics. And now, of course, if I think about the Fermi-derived statistics, there are some electrons with energy higher than W, right? Even though that F is very small, but it's not zero. So what I want to count now is how much energy, how many electrons is flowing out of the surface. And of course, you put a piece of metal there, it flow out. There are also ones that come back in randomly. and at the end there may be some electron hanging around the surface. I'm just looking into the flux coming out. Okay? So the flux comes out. E is the electron energy. Okay? And say outside. And I probably should not. So this is where. Okay, mu. This is one of the. If you look at how we derive the chemical potential, you will see the derivation process is really mu is relative to the bottom of conduction band. And when I talk about work function, is relative to the vacuum level. So there's some difference in the reference point. So that's one place that can cause confusion. So I'm looking at really the for those electrons with the energy above the vacuum level. And those energy, you can think of this kinetic energy inside in the vacuum here. That's the, when I write this more, HK is the momentum, P squared divided by 2M is the kinetic energy. Right? So those electrons here, that's the kinetic energy. And I want to calculate the flux of the particle. I'm not putting charge there yet. I don't like that negative E. Okay? So just a particle flux coming out. So here, because it's coming out with Kx, the wave vector, which is the momentum, is a positive x direction. I don't do both from negative infinite to positive infinite. So now I do this summation. Because I'm looking at flux, so Vx is the velocity in the x direction coming out, and the F is per quantum state. So I'm still doing my counting, right? The number of electrons, each electron has a velocity, and that gives me the flux there. So if you start from here, you do your normal way of converting this way, because this is flux, we should already be divided. That's a typo here. So if you do your normal conversion of the summation into integration, that's what we do here, right? And in reality, because the electron is in terms of wave vector, it's not very large, so you actually can extend those integration really rather than 0 to pi over a, 0 to infinite. So what's Vx? Vx here is a P divided by momentum. So I'm doing that because at the end you can do either energy integration or momentum integration. And in this case, you can say K, I integrate over K is easier, because if I put this, drop that 1, and E minus mu is work function plus the kinetic energy, and you can see if I do this integration, I can actually, because of the summation here, I can split each term and do integration kx, dky, dkz. So that's an easier integration than I convert into energy. I show this because, like I said, the density of states is just a mathematical tool, right? If you use, it's sometimes convenient to use it in energy, sometimes convenient to use just as momentum itself. So if I do this, go rather than 0 to pi over a, 0 to infinite, because this exponential function drops out quickly, this is what I get. Okay? And the exponential here, W is the work function, it's energy, kBt is also energy, right? This is a very small number because W is a few electron volts, kBt is 0.026 at room temperature, so that's a big negative exponent. But the front side, this term, you can say is temperature dependent, And we could write it in terms of T squared times constant. So now I put in, before I said it's particle flux, now I put the charge, because each particle carries negative E, so this is my current flux. Okay? So that current flux now have a T squared, and whatever in the front, I group it into A, right? So AT squared exponential. And this is the Richardson formula. And Richardson got, did a lot of experiment, and he was awarded Nobel Prize for this work in the thermionic emission. Okay? But there are also, if you go to check literature, in fact, Dushman had a paper before him. So sometimes people call Richardson-Dushman formula rather than just Richardson formula. But the point is, we have a T squared, we have an exponential function for the flux of electrons coming out of the surface. Okay, and this constant A is called the Richardson constant. And but say in more general form, because quantum reflection, so this is in fact not just a there's a factor in the front. That's the electron get reflected, even though its energy is larger than the work function, but the waves has always the possibility to get reflected. So that's 1 minus R shows the transmission, and the rest is the this one sometimes you use W, sometimes you use phi. It's all work function. Okay. So, any question here? Yes.
How did he measure that?
How did he measure that? You put the voltage, or in fact, Edison did a lot of work too. This is the beginning. So you say people develop vacuum tubes, right? So you can, in this case, you change the temperature, you measure the current that comes out of the electrode. And what Richardson did different is before, if you go to read the literature, and people do the charge, this kind of thermionic emission, not in vacuum, just in air, in a gas environment. And sometimes the surface is negative, sometimes it's positive, so it made the explanation very difficult. What Richardson did was do it in vacuum, and that made the explanation much more cleaner.
This is just for metal or for silicon?
This is just for metal, okay? And the W is for the work function. Okay. Now, this is where my confusion starts to kick in, and let's think about two metals, right? They have different work functions, okay? And you connect them together, and once you connect them, let's say the charge will flow from one to the other, right? This is mass diffusion. If the chemical potential are different, right, they always at the end will pull together equal chemical potential. You don't have any driving force. You just connect, put a wire in between them. So of course, two pieces of metal lie in contact far away. Each has a local vacuum level, no torque. But if I connect a piece of wire between the two, then the chemical potential is flat. So that means that initially there is a current flow from one side to the other. Okay? And I was trying to think, you can tell me now. I was trying to think now, what's the direction of this current flow? Huh? What do you think? What's the direction of the current flow? Sometimes when I forced to think, ask questions, try to explain to you, even though I can't make it clear, but maybe I can make it clear when we all talk and think. So now I have one piece of metal at larger chemical potential, larger work function, piece of metal, smaller work function. And I connected them together. If I don't connect them together, I think when I put them very close to each other, I know the direction of current. When I connect them, I don't know. If I don't connect, let me tell you, if I don't connect them, but I put them very close to each other, I think the electron will go from the high work function side to the lower work function side through that vacuum gap. Okay. Do you agree? We have different arguments. But when I connect them together, my question was, will the electron flow from the other way? Because that means the question is which one is positive, which one is negative at the end. Okay? Oh, I still don't have a good answer.
When electron travels from the left to the right, then doesn't it increase the Fermi level of the right side? Then
Electron go from left to right. It increase the Fermi level. Well, so this is another thing there. What's really increased is Fermi level. It depends on how you measure, right? I said that the way we calculate Fermi level before is a relative conduction band, right? Fermi level chemical potential is a measure of number of electrons. Okay, maybe you're right. Maybe this is the way we should think about it. And maybe I should say far away, well, the vacuum is the same. And then so this is the because here I have a larger work function. Here I have smaller work function, right? Far away. So when I connected them together, so electron should go this way, the wire. But that's different from what I was saying, right? If I put a vacuum, the electron probably will go this way.
Why?
Huh?
Oh,
why? Because I was thinking somehow those electrons. Okay, these are here is the energy and this is kinetic energy. Of course, you have to, the kinetic energy must overcome the work function. So what's left over here is still zero. Okay, just those kinetic energy just above the chemical, the work vacuum is still zero. Because the rest is used to overcome this work function. But anyway, so if I think this way, if I connect with the wire, then the electron should flow this way. And that's what they were saying. In that way, maybe your reason, so electron now, the chemical potential is raised, but you don't change the work function, so the vacuum level is raised here, local. And then you have, say, so this is the sort of, if I draw, that might be the local, this is the vacuum, local vacuum level, this is local vacuum level. And then my question then, so if electron is flowing this way, how should I think which one is the positive? Yes?
Does it depend on the difference between their Fermi levels and their work functions, how they interact with each other? Because in this diagram, when you connect them, their Fermi levels become the same.
Oh, after you connect, the Fermi level has to be the same.
Right. So the work functions, depending on their differences, you could have no flow or flow in either direction.
Yes. But see, I'm drawing a schematic where I have one side as a larger work function. So now this work function is already relative to Fermi level to vacuum level, right? So my question is which side is flowing?
So
smaller the W, the bigger the current.
Okay, so you're right. So the small, okay, that's a good way to think about it, I think.
So that's kind of.
So the larger is the W. Okay, good. So maybe this will be consistent. The larger is smaller W, more flux going this way, and higher is less flux. So at the end, you will have more electron on this side. So this will be positive, this will be negative. And that's consistent with my connecting a wire. Okay, now I agree. Thank you.
The local vacuum level is shifted by the electrical potential.
Well, that's the, so, okay. Once you got more electrons here, right? Now you think about, this is the electric field, the direction is this way. Right? That's your electric field direction. And then you will resist the further going to the other side. And then you draw your potential. Now if you say electrostatic field equals the energy, which is the potential divided by charge, which is negative. So when I feel this way, that means this phi here is higher, phi is lower. That means the energy is higher, energy is lower. That's consistent. It's just this E, you have to think about the voltage opposite to E, to the local energies because of the negative charge. That's where I really don't like. Every time I draw those diagram, I have to say, electron is a negative, how I'm going to draw. Whether I'm draw potential, they're really, okay. Here we have energy, or E, when let's talk about the electron energy or local energy. But see, when I talk about voltage, I talk about electrostatic potential. And electrostatic potential is really divided by charge. U divided by Q. This Q for electron is negative E. It's got to reverse the sign. So when I draw this way, as the potential, right? I'm drawing this work function. That's an energy unit. So when I draw the electrostatic, I have to reverse this way. So this has a higher electrostatic than this side because of negative electron. Okay? That's where the confusion every time I have. Okay, but I do want to mention this. So now, clarify the question. So you get a W, so that's the W minus W prime. So really this negative E is because I did W on this side, I put a positive electrode, a negative electrode, and I should measure negative voltage. That means this positive, this is negative.
What does the dotted line mean? In the figure, we have a line in the middle.
Oh, that's not my figure. I should have cited this. I forgot. This one was from Ashford Merman. Okay, so what it's saying is that you are changing in terms of the electrostatic energy. Because this is a chemical potential, and there's also electrostatics. So here, the voltage is positive here, but for electron, the electrostatic move up.
But in the upper figure, isn't it true that the right side should go up so that the work function level should be the same?
Work function doesn't change. Work function is you pull an electron from metal immediately out to the local vacuum.
So when electrons are out from the two metal,
right,
then the energy of the two electrons should be the same.
No, that's the point. That's what I say at the beginning. You have a local vacuum. Okay? Once you see, once the electron goes from this side to the other side, right, you raise, so here is positive, here is negative, so the local vacuum, locally on the surface, here, metal surface, there is a higher electrostatic potential than here. Okay? So the local vacuum level varies
But in your figure in the middle,
Yeah.
the highest level that is the work function level that is the same. It's different from.
No, what I got there is thinking at the beginning, far away, no talk to each other, right? If you put together and start talking, you have local electrostatic influence. You will create the imbalance in the field, electrostatic field.
Okay, I see. So the upper figure doesn't mean that the two.
There's no talk. This is just a random because you really can't align. Okay. But this is where contact potential is. This is actually defined as the contact potential. And I say this because it turns out that very often we want to measure the work function, and this is when I read, I suddenly realized this is an easy way relatively easy seems to be to measure work function. And one way to measure work function is just measure the contact potential. You take a standard piece of material where you know the work function, and then you come close to the other piece, and you start to have current flow. Because when you close it, right, and your potential is the same, but when you change distance, your current, because if you think of a capacitor, you'll start to have current flow. And that's the so-called Kelvin probe. Kelvin method actually measure the contact potential, and using that, if you have a standard piece, you can measure the other contact potential. And I think a Kelvin probe is standard accessory if you buy atomic force microscope. You can add a few $1,000 and then we'll have a Kelvin probe software there. Okay. So let's move on. Now I'm thinking about really the diode. That's what I draw on the board. And again, I draw a higher anode and a lower work function cathode. So in this case, right, just as we discussed, you have a local vacuum level higher, and then eventually the chemical potential is flat. Okay, and at the equilibrium, right, at the transit, they will have current, but eventually you establish equilibrium. So this is the normally this is the cathode current going from left to right, and this is the anode current from right to left. And you can say I did not just do WC, I do a WC plus EC. This is because I'm thinking about the steady state. I'm not thinking about the transit, initial establishing equilibrium. So you can see once you got a potential, the electron from here cannot really go here anymore. So only the electron with the energy, even on this side, with the energy higher than this point can go to the other side. Right? So at the end, you get the, at the equilibrium, the difference of the two is zero. There's no net current flux. You put two pieces of metal together, you connect them, rather than just the initial current, at the end it should be no current flow. Otherwise, you get a perpetual motors, right? So that's the vacuum at the equilibrium. Now I'm going to put a temperature difference across it. Right? One side is hotter, cathode I made it hotter, anode colder. Okay? And of course, I still have the current. And if I write the Richardson expression, okay. Now in this case, if you think about it, when you heat it up, there should be more electrons getting kinetic energy, higher kinetic energy, higher temperature. So electron will go from cathode to anode. Right? So electron, there some current to go here, and so eventually, relative to speaking, the chemical potential will no longer be the same. And really, this chemical potential is electrochemical potential. Because what I add here, the voltage that's generated added to chemical potential, so this level is electrochemical potential. And that's what I can measure. When I put the two electrodes, I'll measure a voltage difference, and that voltage difference is these 2 points, voltage difference. Okay? So because of that, my current, cathode current, now this is what I originally have, and this is the additional, and again, this is where I don't like it, because I should have put a negative sign, right? Because if you think about the electron here now, the electron that needs to go over this, so from electrochemical potential mu C to the maximum point is the distance shorter. And I put a positive sign here, so ideally I should get the negative solution V0. That's my open circuit voltage. Okay? And I don't think I get that. I still don't know why. My sign doesn't seem to be right. Okay? So I give you the challenge. You go back to sort it out and come back teach me. And this is the cathode. This is the anode. And of course, at steady state, if I don't put any connectors there, I have a voltage difference between the two. Real voltage that I can measure, right? So the again, this is related to the negative charge, and the equilibrium. I should not say at the equilibrium, at steady state, not the equilibrium. When you have temperature difference, you have chemical potential difference. You don't have equilibrium. Accurate way to say is at steady state, right? At steady state, there is no net current flow because I didn't connect it to any load. I have open circuit, so current is 0. So if I go through these steps, put these two expressions, right? This one minus this one is 0. So I'm going to do that. These are the two terms, right? And I take the ratio, I take a log, get rid of my exponential. Second step, I was hoping I get a negative sign, but I don't get it. So you tell me where I should get it. I didn't say I get a negative sign. Okay? Right? I still don't know why. But anyway, the magnitude is correct. The sign, somehow, I don't know. But let me also look at this and point out that if you think about before, when we talk about feedback effect, it's voltage divided by delta T, right? So if I do a voltage divided by delta T, not delta T, just an order of magnitude, this term I put it in here, and here is KB divided by E, 2 KB divided by E. That's of the same order of feedback coefficient. So this term actually comes from, is very similar to the thermoelectric. And this term is the thermionic term here, because it depends on the barrier height of the anode barrier height. Okay? So that's the open circuit voltage. And of course, open circuit is useless. You don't generate any power. You have maximum voltage, but you don't generate power. This is the same for photovoltaic cell, right? So you need to put a load here. Once your current starts flow, you don't get that high open circuit voltage anymore. You get your actual voltage. That's the actual voltage. And you can change this voltage by changing your load resistance. That's a load matching. That's for all solid-state devices. Solar cells, thermoelectrics, thermionic. You have to optimize your load or optimize the device itself to match internal and external. That's load matching. Okay? So if I rewrite the expression because the contact potential is the same as WA, and you can say my current depends on the voltage, and of course power is just current times voltage, right? So that's my unit volume power, unit surface, I think, because J is the surface. And so that's the power. Now, for thermionic generator, I have to do the efficiency. So I have to look at how much heat transfer happened. I have now electrical power output. I have to look at how much heat transfer. So what are the mode of heat transfer? Here, you look at this. First, this side is hot, this side is cold, there's radiation. Any other heat transfer?
Electron carries.
That's right. Right? Or just we don't forget electron also carry heat. So first let's look at that's a fundamental side. Right? Radiation is not lesser due to electron. It could be due to lattice. But electron, when you have charge flow, you always carry the heat. So I have to count that part of heat. So this is the first step. What's the kinetic energy? That's the right, the 1/2 mv squared. So this is a p squared divided by 2m. That's the kinetic energy above the barrier, right? So I do my integration the same way I did before, as I do particle flux. I didn't start from beginning here. I just write the expression, and I do my integration. And it turns out the heat flux, kinetic part of the heat flux, is proportional to current flux, and 2 kVe, that's the Seebeck coefficient, times T. So Peltier coefficient, remember in the thermoelectrics, Peltier coefficient equals Seebeck times T, right? So you can say this is very much the Seebeck part, is the Peltier Seebeck times T, times current. So this is the Peltier heat carried by electron from cathode to anode. But the heat is more than this. Because remember when we define the heat is the energy minus chemical potential, E minus mu, right? Relative to chemical potential. So relative to chemical potential, I have this part is kinetic energy, then I have really from here to here. This is the cathode side, right? The energy, the one that really go over the barrier, the rest is from here to here. So that's my W over E minus V here. So this is from here to here. That's my potential part. This is the 1/2 mv squared part, kinetic. So that's all the heat it carries. Okay? Right? What is this in terms of resemblance? If you're a mechanical engineer, think this. Give me an analogy. Huh? It's the evaporation of water. Right? The water molecule coming out of the surface carry a lot more energy because you have to say the energy is say every other. So if you think about the water, right? And there are some molecules hanging around. If I take out the molecule away, and then there's another molecule we created behind. And the creation of this molecule from the liquid phase to the vapor phase is the latent heat, right? Essentially, that those terms, this are the latent heat of the electrons when you come out of the surface. And this is the kinetic part. But at the end, although I say this, I still have a little bit of trouble thinking this as an evaporation process. Because I'm trying to think about an analogy of, okay, here is a potential, okay, the bottom. You come out here, so that's the minimum. So each molecule carry out this. I say that's an evaporation process. But what about suddenly a bottle, okay, what about this process? If I have a high energy electron in the potential here, suddenly fall off a cliff, and that's excess energy, potential energy, do I consider that as an evaporation process also? Then I'm a little bit confused. Whether to think of mechanical. I don't quite know what's the whether I can give an analogy of these two different processes in terms of evaporation. And this one is more to me somehow. To me is I have a container of liquid. I open a hole. This is a high temperature. When the liquid comes out here to the other side, the vacuum, it suddenly evaporates. Change from liquid phase to vapor phase. I'm making this to this and this to this. You can tell me whether you agree. But at the end, I'll give you one example where I struggle on this question. Why I struggle on this question. Okay. So that's electron heat, right? And of course, there's also another side from I have to reverse this. This is from anode to cathode. This is from cathode to anode. And the difference gave me, this is the electronic part of the heat. That's the first two. And then we have radiation part. And then you have a lead. That lead conduct heat, so that's a conduction heat loss. So if you have real device, you have to consider all those heat losses. Okay? And of course, the efficiency is defined as the power out divide the heat in. Always what we do when we do efficiency. And if I do most ideal situation, I neglect radiation. Why you can't neglect? Say, well, I have my perfect photonic crystal, no radiation. It's impossible. But say, I make it small. Okay? So if I neglect all other heat, just by the electronic part, I cannot neglect it. Intrinsic. And that's the curve you will get. And this time I remember to cite the reference. And you can see in terms of the efficiency you can get, it's very much a EVA, that's WA. EVA, V is the voltage, so it's W work function of the cathode anode side divided by kTA, so that's one parameter. And you optimize this parameter, and this is the ratio of the hot to the cold to hot side temperature. Okay, so that's the ratio. So you can see the peak efficiency, pretty impressive, all right? Very high efficiency. Of course, this is when you neglect the radiation. You can't get rid of the radiation part. You also have additional heat loss. But compared to thermoelectric, because you're using vacuum, so you don't have full-on heat conduction, that's why this can give you a high efficiency, theoretically. And the first experiment was done by Astapoulos. Some of you are from that lab. Okay, he was he did the, this was in the 50s. So he came from, he told his story, he came from Greek and trying to get the topic, and he were able, at the time, the SIPS didn't have really research government funding, but somehow he were able to get some funding to do the thesis. And he did a thesis, he went out and opened a company. He had a very nice book, Thermionic Energy Conversion, 2 volumes. I was reading some of it, I couldn't read all of this, but very detailed. They actually talk about the detailed electron. I'm very impressed. Talk about from basic quantum mechanics to work function, and that's Astabulus and Giftobulus. Giftobulus is still Professor Emeritus in nuclear engineering. So they wrote the book together. And you can see they did an experiment, 2300 F, very high temperature hot side, and cold side is 1000 F. That's the challenge with thermionics. It's a very high temperature device. Okay? And the efficiency was, at the time, 1958, it was pretty good, right? 13%, 14%, right? Pretty good efficiency. And so the very ambitious here, he also put his voltage negative, and you should read this paper. I'll send that as a reading. So his story is he was a faculty member in our department, and he went out to start a company, assistant professor with the MIT, start a company. That's called the thermoelectron. You go 12895, you'll see the sign thermoelectron. Now it's called the thermal feature. And by name, they were trying to commercialize this. The story is he told me he went to Washington on Washington trip, and then he realized NASA, the business really depends on whether NASA flies or not. And so he changed the direction. Good for him, I think. Otherwise, Thermoelectron, he says. And the company, Thermoelectron, really does a lot of instrumentation. So it's no longer doing really thermionic energy conversion. And the recent merger is now with Fisher. Fisher is another big company there. So now it's Thermoelectron, Fisher Thermoelectron. Okay, that's a good story. And the real device was not as simple as I drew, of course, the high temperature, but also there is really a fundamental problem. This is a fundamental problem, is charging, right? If you have an electron in the vacuum, well, any electron, any charge, surrounding charge, there's a field. A charge there will create a field, right? So when you got a lot of electrons, they will create electrostatic potential. And this potential distribution, you can see now I draw rather than a linear one, and really depends on the gap, depends on the charge number. But the point is, now your barrier is higher than just work function. You got an additional barrier to overcome due to space charge effect. So this is a big problem. Space charge is a big problem. And in addition to this, there are also many other problems. Of course, most mature work functions are very large. That means you have to operate at higher temperature. Few electron volts. If you check, most mature metals is about 4 electron volts. There's some material like as low as 2 electron volts. So if you use the cesium is actually you can first you can generate cesium to neutralize positive charge cesium vapor to neutralize the negative electrons. So it reduces the space charge. But cesium is very corrosive. So there's problems. Chemicals at high temperature. And you can use either vacuum or Or there are other modes where you just put a gas in between. When you put a gas, there's plasma formation, so there's this vacuum mode or plasma mode of operation thermionic devices. But historically, think about this. The transistor, the diode, the solid state were invented in the 50s, right? And before that, computers were built on vacuum diodes. The vacuum diode is essentially this, except they operate near room temperature. And this is just one side that operates at high temperature, the other side low temperature. Problem is they go to 1,000 degrees. Okay. What are the recent trends? The research in this is relatively small, I see. Russian actually put this in space station. I tried to dig out a picture, I couldn't find one. But they call it Topaz. And so Russia had a few space missions that use thermionic engines rather than thermoelectric engines. You can search whether you can find more information if you're interested. And so some of the idea people explore why the negative electron affinity. So if by maybe electron just jump out itself, right? Negative electron affinity. Vacuum level is lower than what's inside. And so that's one, and people still look at this. And the other is a small gap. And this small gap, there were actually some programs that the gap goes to angstroms. It's crazy in the sense, of course, in that case, what happens is the electron can tunnel quantum mechanically from hot side to cold side. So you don't have this space charge limitation anymore. Electrons don't have to have an energy higher than the top of the electrostatic, right? So you can really just zip through. When this one is of the order of angstroms, that's a scanning Common microscope principle, right? Electron can go from one side to the other tunnel through. But say, like I said, that's pretty technologically is too challenging because think about the maintain hundreds of degrees at angstrom level, right? And then the most recent is solid-state thermionic, where you run into still the heat conduction problem, right? Once you got the solid, everything solid state, you have heat conduction, so that's the same as thermoelectrics operation. But I just want to give you one sketch on the what does the electric electron affinity mean? Because normally you can see the work functions here between chemical potential and vacuum level. That's work function, and of course the space charge creates a higher. And the negative electron affinity still doesn't mean electron will all fall out of metal. You don't get the metal anymore. Here is the bottom of conduction band. But this is say in negative electron affinity, which is typically semiconductors, very wide gap semiconductors. The electron actually sits in here. More the Fermi level is here. So it does not come out, so you still need to overcome the space charge to come out. So that's the liquid electron affinity material. So people have interest in this, not only for thermoelectrics, and not thermionics. Okay. So that's a discussion on thermionics. Richardson formula, what's important? Yes?
You said that people try to create some active material.
Right.
What happens if we just put some dielectric material instead?
Dielectric material, yes. The problem now you got a heat conduction. Right? So run into the classical thermoelectric problem. And what we are now, somebody asked, say, semiconductors. And let's think about now we have a metal and a semiconductor, right? You always have that in any microelectronic device, because at the end you want to make a contact. You put the metal on the semiconductor. So that's a typical classical situation. And now let's see what happens. And of course, here is the Fermi level, here is the semiconductor Fermi level. I'm talking about the along degenerated, so Fermi level is in the gap. This is really where electron sits in. And when I put these two together, I still got the same problem. If I connect them electrically or put them in contact with each other, the chemical potential difference will drive the charge flow. So eventually, the chemical potential on the two sides will be the same. That is always the driving force for diffusion, mass transfer. Charge is mass. Mass transfer is chemical potential. Heat transfer is temperature, right? Mechanical is pressure. So, thermodynamic quantities. And when I put them together, so the Fermi level align to each other, chemical potential align to each other, eventually. That's a driving force for charge flow. And here, the work function, here is the affinity. And then at the point of their contact, you can think that they have to have the local same vacuum level, right? Same vacuum level. At the point, if I put these two pieces together, locally, I pull an electron out to vacuum, that's the same point as the metal side. So there is a mismatch between the work function and the affinity, and this mismatch is delta here, which you can check, right? For different material, you can always find, not always, sometimes the people have measured it, but in theory, you can find this. Okay, so there's delta. That's the this delta is the Schottky barrier height, right? That's the barrier height. There is a potential difference of the electrons in the semiconductor and metal side. Now, of course, if you think about this, electrons are here. So this electron will fall into the metal side, right? Electron go from high energy to lower energy. Anything go high energy to lower energy. So once they fall, there is positive charge, less electron here. So chemical potential is measured between EC and here. And less electron means larger distance. So you can see here, I'm going far away from the interface. That's my bulk region. Interfacial region, the semiconductor side, there's a band beneath. EC is no longer flat. Okay? And that's because intuitively electron fall on this side, less electron, so bigger separation there. Yes?
The Fermi level,
Same.
level there?
Yes, I didn't draw it. Level.
So the vacuums are different?
Vacuum now.
It's different.
Vacuum.
It's going down.
Yes. Thank you for telling me that. Vacuum level is different.
So is the drop in EC on the other side because EC actually falls down as well?
So locally the vacuum level also changing. So this is where again you have to really think. This is defined really local. The sort of this rule is actually sometimes violated. And particularly when you put the two different semiconductors, you first think about the vacuum level, then look at the affinity, and that's the band edge offset. Doesn't always work.
Because I'm trying to understand, so if delta is before you bring them into contact, you have EC between EC and the Fermi level.
Right.
Metal, right?
Right.
So that's the original delta. When you bring it together, EF and the vacuum drops down for the semiconductor, then EC drops down as well. Is that correct? So that's why it creates that curve.
Does the vacuum level change? Let me draw the vacuum level. What I saw of the vacuum level here. this is the vacuum. Let me draw. This is the metal side, and this seems to be the semiconductor side. And this is the EC, and here is the here is the work function. Here is my electron going to vacuum. So this is my affinity, right? The difference gives me delta. Okay, so I didn't have that jump in the vacuum. Locally, I put it same. Okay. So this is the this kind of interface here, right? Is often between metal and semiconductor. And this is the Schottky barrier. And now, if I think about the flying flow electron, I talk about contact, right? You apply a voltage, how the electron flows. Okay? And of course, you can always say, again, from left to right, right to left. Same kind of thinking there. Okay? And here is a p-type. Right? So before I draw electron, and here is a pulse. Pulse is this from here to here is barrier. This is a positive charge, say holes, and here there are less holes because the electron fall into here, neutralize, make less hole. Really, is the electron fall into where I'm confusing. Think about so positive. So really okay. So electron should fall into this side from here to here because the electron is at a higher energy than the here. So electron fall into this side. There's less hole here because electron fill in the empty states in the holes are just what's left over the empty states of electrons, right? So what's hole? There's really no hole. In the valence band, this is the EV. The electron field over here and left behind a few empty states. Those are the empty area. Now the metal electron from the metal, right? Electron from the metal fall into this side, fill in some of those empty states. So this is no longer available for hole. So this is less holes states. So there are less holes here. This is less hole. So the Fermi level between the chemical potential and the valence band becomes larger. So this is the Schottky barrier for the p-type. Yes.
So in the p-type case, actually, so in your figure, actually, for the p-type silicon, actually, the vacuum level will go up. It seems like it goes flat.
Vacuum level. I didn't draw a vacuum level here.
The green region.
Where is it?
I mean, you have the EC, and going up is the vacuum level.
No. The p-type has to be. You have to look at the. I think this is your W on the metal side.
Yeah.
And you have to think about this will be here, right? And so from here to vacuum level, vacuum level here, and now electrons start to fill in because the electron go from high energy states to lower energy states.
Yeah, so you mentioned the vacuum level. That's why.
So the Fermi level will be because this is p-type, right? So the p-type will be going here. This is Fermi level. So this is the this will be the.
The EC also going up, and the vacuum level also going
No,
up.
EC doesn't go. This one, EC, the background has to be same. So between here and here, EC has to bring down.
Oh, you mentioned that.
Yeah. Okay. there are not much electrons in the p-type. So you say why the electron doesn't
And the
go?
vacuum is random too.
Huh?
The vacuum is random too on the semiconductor side.
Vacuum also has to bend down, yeah. Okay, so this is your vacuum level.
So it seems like going up.
Huh?
That's exactly what I was telling you. It seems like going up.
Oh, vacuum, I see. Yeah, vacuum is doing. I thought that you were asking the EC. Okay. Very tricky. Good. Now let's say I'm giving you the formula. I'm not deriving, but the point is it's a Richardson formula, right? Like what we wrote for vacuum. And but there is some difference also. So the first factor here is the same Richardson factor. And then I have this exponential EV kBT, and you can see that that depends on whether my voltage is positive or negative, right? So when I see positive, is I raise the Fermi level on this side, on the semiconductor side. So the voltage is applied. So this will be, in this case, this will be positive electrode, negative electrode. Raise the electron on this side. And of course, electron raised, so there is more chance for this electron going from left to right. From right to left. Right? So that's where my EV kBT comes from, exponential. So I have this forward bias. Now when I reverse bias it, okay, let's say when the electron go this way, it's really charged go this way. That's what I draw. This is a positive, metal is positive, semiconductor, and is negative, right? And when I reverse bias it, this direction, that barometer is fixed. Didn't change. So this current is always that first, this is saturation current there. Right? Now there is less going this way, but that's not much less because you see here, that difference is small. So now this is the same as a diode, right? Bias differently, you have, say, different current characteristics. So that's similar to a diode, typical diode, and this is a Schottky diode. Positive bias, negative bias, saturation current here, not zero. And this is when you bias too much, it breaks down. So you can just punch over this barrier when you're under not reverse bias. Okay. You can see metal semiconductor interface, and if you make a contact like this, it's not good. Typically, you don't want to make a Schottky contact. Right? And how you solve that problem? And the way people solve this problem is they dope it very heavily. So let's say you'll say when you dope heavy, this becomes so basically when you dope very heavy, few electrons come over, this is very narrow, this is very sharp. So when we draw, this becomes very sharp when you dope heavy. And when it becomes very sharp, so electron come through rather than have to go over the barrier. Okay? So that's one way to overcome the Schottky resistance here. Otherwise, you'll say, so this is how people make atomic contact. Is you dope the region very heavily. And of course, you want to use the right metal to start with. so that the work function, the delta here is not large, right? So that's why if you want to make a contact, you want to know your work function, you want to know electron affinity of the material. And of course, there are many other reasons where you don't make a good contact than this. You may have a physical lung contact, a vacuum gap there. That could also, vacuum gap is essentially a very high barrier, right? You have to tunnel through that. You can tunnel through that. Or if it's too wide, there's no chance you can go through. Okay. Schottky diode. Since we're talking about diode, I'll continue. Right? This is a metal semiconductor. A regular diode is not a metal semiconductor. It's a semiconductor diode. So let's look at semiconductor, right? So we make a semiconductor N-type, semiconductor P-type. And put the two pieces together, contact, same thing happened. Right? The chemical potential must align each other. Right? So what that align looking like, what really means is here N-type got a lot of electrons, so electron go this side. P-type I got a lot of hole go the other side. Okay? And so when electron go from this side to this side, what's left behind? Positive atoms there, right? So what you have here is positive atom. This atom do not move. Those atoms are just charged there. They don't move, right? On this side, holes left, so they are left behind. Really, it's just get a holes left is like you get an excess electron to for this case p-type or boron. Is say you get an excess electron to the not quite neutral now in this region. So those, when I draw this, is ions, positive ions, negative ions on the two sides of the interface. That's a space charge region, not a mobile ion, mobile electrons. Okay. And if I draw the band alignment, right? So if I forgot, EC should be mu. No. This one, there should be a line here. That's a EF. It disappeared. Right? This is EF. And this EF and this EF will have to align each other. So it's easy to think about the connection. Right? If I have far away from the interface, I have an N-type. And far away from the interface, I have P-type. And now P-type formula was close to EV, N-type formula was close to EC. And then connected in between, right? And at the end, it's equilibrium. That's your P. And in between this region, a space charge region. No charge there. No free carrier. No electron, no holes. Just a positively ion, negative ions. Right? Okay? And that means I got now I have positive ion, negative ion. I have a potential, right? Pointing from positive to negative. So that potential is built-in potential pointing negative to positive, and this potential will resist further diffusion. So at the end, you got the equilibrium. So this is the built-in potential that resists diffusion of charge from one side to the other. Chen junction form. Now let's look at what's the current voltage characteristics. Very similar to Richardson formula. So I'm going through this. That's what you learned before. So this is I threw at you. Okay, right? Electron number density, hole number density, and if an electron in any semiconductor, right? If you write the electron, you can also derive similar hole, and then you take the product, you found out the product is constant. This P and N. So if you dope the electron, dope for N type, there are less hole because P times N is constant. Okay? P times N here is related to band structure, effective mass conduction, effective mass valence band gap, and KBT, right? So P times N is constant. That's the now how I calculate built-in potential. From on this side, I can say, because I know this is constant, so I just need to calculate this. I need to calculate this, and the difference is this. That's the built-in potential, right? So from look at this side, I have EC minus N. That's EC N minus mu. That's this distance. So I can start from the. Let's suppose each of the donor, each phosphor, for example, I put in, give me electron. And I reverse it, I get this. And I can do the same on this side. I given the number of the acceptor, that's the number of phosphor, boron I put here. Each boron create one hole. So I find the distance between here and here. This is from, I already converted it into EC. That's from here to here. And now this from here to here, that's here, that's here. The difference of the two gave me the built-in potential. So this is the built-in potential, and it's the acceptor donor. Acceptor on this side, donor on this side, how much I dope it. So the more I dope it, the higher is the built-in potential. Right? How wide is the space charge region? Now that you can solve Poisson equation. I'm not solving. I'm just giving at you. Okay. But I want you to look at this. If it's just the electrostatic, this is the width of the space charge region. Okay, and it depends on the dielectric constant. Larger dielectric constant, wider is the space charge region, right? So if I look at this one side, either acceptor or donor, that's roughly how wide it is. And that's why I said I want to dope heavily to reduce the Schottky effect for contact. If you can see that if I dope heavier, the width of the space charge region is narrow. Okay? And this is where you will talk to people with intelligence. They say, oh, what's the bi-length? That's essentially a measure of the weight, intrinsic weight. Okay? And the bi-length is essentially what we have here, replace built-in potential by KBT. The spread, thermal spread, right? So, heavier doping, shorter is the space charge region. Okay? Some people do nanowire surface effect. Depends on, you can see whether surface effect centered or not. Depends on your doping. So the bi-length. Okay. Finally, I want to show you this because it's the same as Richardson formula. Right? That's a PN junction I times B. Current voltage relation. Except JS. And that has a lower price there. The JS is no longer AT squared. Right? That exponential very high. no longer the Richardson form. And what we have here is diffusivity of hole, diffusivity of electron, recombination time of hole on each side with the electron on each side. So this is a complete different mechanism. And so these are the definition. Here, I'm going there quickly, but I want to chew on it and come back and we'll explain more. And basically, this is a different. Here, you can see the formula is the same, right? Saturation current Js is different, but it's a complete different mechanism in terms of transport. Because in a pin junction, the electron, when you go from this side to this other side, there's no electron anymore. Right? P side, there's not much electron there. So how the transfer happened? And it turns out it's really the hole recombine with the electron. So the whole sphere recombine with that electron, and then hole has to keep supplying. So there's so in a p-n junction, it's a recombination that's important. That drives the current flow. Or in a Schottky diode, it's just the electron go this side, electron go this side. There is no supply issue there. So one is a majority carrier device, the other is a minority carrier device. Very different. Okay, formula is the same. Almost the same. Okay, so just last slide. Like again, I want to show. I'll come back to do a little review, but go think about this. So this is the electron current, hole current, and they add up to the total current must be continuous. That's a p-n junction. Okay, and what most people do not know, even electrical engineer, I'm pretty sure, is that inside the junction switch charge region, there's no heating. In fact, it's cooling. Okay? You look at the Peltier effect. You go to analyze thermoelectric effect in the semiconductor device. You find out that in the space charge region is a cooling effect, and it's really the recombination outside the space charge region that created the heating. Of course, heating is a big issue in microelectronics, right? But in a diode, the center, the interface is actually cooling effect. Okay, I'll stop here. And I think there are a lot to think about. Again, a lot of materials.